All right, good afternoon. Thank you for joining me. This is Sean here at Zycel out of sunny Southern California. Today we're doing our Wi-Fi 101 webinar. It's been a while since I've done one of these. This is a presentation that's kind of, for the most part, a high-level overview of Wi-Fi and how it works. And this presentation came about just because we found that, Wi-Fi is one of those things where everyone's using it, but not a lot of people know how it works, including me. Um, and it's one of those things that's completely invisible and doesn't always seem to be making sense. So I put this together a couple years ago to sort of give you the basics of how Wi-Fi works. So as we go through, if you have questions, feel free to use the chat function to send them in, and I'll do my best to answer them. And yeah, we'll go ahead and get started. So just a quick brief background slide here. Zycel has been making networking equipment now since 1989. We were, I believe, the first consumer router with NAT functionality in it. Those of you that were around in the dial-up bulletin board days and dial-up internet days will remember us from our battles with US robotics about different types of analog modem technology. And right now we serve 150 different global markets. We've shipped over 100 million devices. This slide is a little bit old. I should probably update this to one of the newer ones. But yeah, so we've been doing this for a while. In the US, our main focus has historically been the telco side of things. So selling things to large internet service providers, CenturyLink, Lumen, whatever you want to call them, those types of accounts. So we have been making Wi-Fi products, and specifically Wi-Fi products aimed at the channel since 2000-ish, 1999, something like that. We had some original 802.11 PCMCA cards when I joined the company that weren't even 802.11 A, B, or C. They were just strictly 802.11. So that's how long we've been doing it. However, in the US, we haven't made the really big push that we have in some other places around the world for our channel products. So unfortunately, we still don't have sort of the name recognition when talking to the general populace, as it would be nice to have. So anyways, on to our Wi-Fi 101 presentation. So I just wanted to sort of cover here the sort of timeline of the Wi-Fi different standards that have been out there. So you can see here, Wi-Fi got started all the way back in 1997 with 802.11. 1999 saw 802.11 A and B. And then we've had various new technologies over the years. And as you can see, they come in sort of spurts and sputters. We got a 2-year gap between 802.11 and 802.11 A and B, a 4-year gap to get to G, and then a 6-year gap to N, 4-year gap to AC, another 6 years to AX, wave 1, then 2 years after that, wave 2, and then just 3 years after that, Wi-Fi 7. And it's getting faster. So Wi-Fi 8 is just around the corner. Now, the timelines I've put on here are basically when these standards have been ratified. One of the things we have seen out there is people will be shipping product long before IEEE gets around to certifying the standard itself. To give you an example of this, people at January at the CES show were pitching products or showing off prototypes of products that use Wi-Fi 8. Wi-Fi 8 is not expected to be standardized until 2028 or 2029. And you will probably see consumer-oriented products calling themselves Wi-Fi 8 by Christmas this year. So that is something to talk about here, is that there are different players in the space. So IEEE is who creates this standard, and it goes through a very long and complex process of different drafts and votes and things like that. And then there's also the Wi-Fi Alliance. The Wi-Fi Alliance is who gives us names like Wi-Fi 7, Wi-Fi 6, etc. So they did that from a marketing perspective because, you can't expect the average person to know which is better, which is newer, A, B, G, N. So they gave them names to make it easier to keep track of which generation is the latest. The Alliance itself is a combination of manufacturers, chipset vendors, and even some retailers that are focused on marketing Wi-Fi and making sure everything is compatible between different Wi-Fi devices. That was one of the challenges in the early days of Wi-Fi. was that there's different ways to interpret rules or laws or anything else that man writes. Um, so there's different ways of interpreting things. So one company may interpret it one way, may company may interpret it another way, or you run into situations where somebody just decides to skip certain things or not implement certain things that they're supposed to. So the Wi-Fi Alliance was there to help sort of force compatibility. I know in the early days of the iPhone, we had a lot of issues with Apple wasn't following some of the standards when it came to Wi-Fi with how they'd implemented it. That broke compatibility with a lot of other people's products, as an example. And then there's the FCC. So the FCC is the US government. So they control the radio airwaves and set the rules for using radio airwaves here in the United States. Um, so they'll tell us which frequencies you can use, what power you can use, how you need to behave in certain situations to be able to use a device without needing to buy a license. So those three people all sort of come together to give us the product itself that we know. So we were shipping Wi-Fi 7 product, long before the IEEE had finalized the Wi-Fi 7 spec. And you will continue to see that. And that's just because the spec is, 97% done. And once it gets to that point, it can still take up to 2 years or more for them to finally officially ratify the product. But usually it's good enough that the chipset vendors have been able to make products based on it and start shipping those products. So Wi-Fi uses radio waves. So as I mentioned, the FCC is who's in charge of that. And some good things to keep in mind here is basically as the frequency goes up, the easier it becomes to cram more data into it. And as frequency goes up, the lower the range. So I'm definitely dating myself here, but to give you some real world examples for this, when I was a young kid, cordless phones operated in the 900 megahertz space. I think there may have even been some 700 megahertz stuff back then. And those phones were great because you could literally walk out of the house and walk over to your friend's house across the street on your cordless phone, and it would work great. And then sometime in the late 80s, early 90s, there was a big push to move to 2.4 gigahertz because 900 megahertz was a very limited amount of space. Sound quality wasn't all that great. So by going up to 2.4, you could cram more data on there so your voices sounded better. You also, if you were living in a condo or apartment complex or near one, the old cordless phones had issues where there wasn't enough channels available, so you would hear other people's conversations. So 2.4 opened up a lot more bandwidth for people to use, but the range decreased. And then in the mid 90s, 5 gigahertz in-home cordless phones became super popular, and people started running into issues where now with 5 gigahertz, if you had a larger house, you might not be able to use that cordless phone in all rooms in your house because the signal couldn't travel as far. And that's just because, again, as the frequency goes up, the range goes down. So in order to broadcast radio waves, you need a license from the FCC, and the FCC has different rules based on what chunk of frequency you want to use as to what sort of license you need to get and how many hoops you have to jump through to get that license. So one of the things they did do is they've opened up different chunks of spectrum that you don't need a license to use. And that's where Wi-Fi operates. So Wi-Fi uses these unlicensed chunks of spectrum. So initially it was 2.4. So initially back in the day before Wi-Fi, it was 900 megahertz. And you can still find some specialized wireless data technologies that still use 900 megahertz. But 2.4 is where Wi-Fi really kicked off, and then 5 gigahertz. So those were the two main spectrums that have been Wi-Fi for lots and lots of time. And then, a few years ago, they finally opened up 6 gigahertz for us to use. And we'll talk more about 6 gigahertz later. So just some basic background. When you're talking about radio waves, power is measured traditionally in dBm, so decibel milliwatts. Every 3 dBm increase doubles the output power. So for instance, 23 dBm has double the power of 20 dBm. So we've got a little chart here converting dBm to milliwatts. Milliwatts is what traditionally you would tend to be seeing on consumer-oriented products, especially back in the day in the early 2000s. You would see that a lot versus dBm, where dBm is what you normally see on business class products and what you find on data sheets rather than milliwatts. And there's a couple reasons for that. One is if you're calculating a link budget, You need to calculate how much power is coming out of your Wi-Fi chip. You need to calculate the amplifiers. You need to calculate amplification from antennas, which is measured in dBi. You need to subtract loss for your cables. So all of those things can easily be added together to give you a nice round number. Consumer products preferred milliwatts because it looks better, right? If you're buying a product and you're comparing from one vendor to another, one claims 200 watts and the other claims 100 watts. So obviously you want 200 because that's a huge difference. Where if you're looking at DBM, the difference between 20 and 23 doesn't seem like that much. One of the other challenges we run into here, and we'll talk a little bit more in a future slide, is that double the output power is not double the range. It's not even close to that. So that's another thing here that we'll talk about coming up here. So it's a misleading number to use because it makes it seem like the performance difference you would expect should be a doubling the performance, and it's not. So when we're talking about radio waves, probably one of the most overlooked things that affects the quality of Wi-Fi performance is the signal to noise ratio. Basically, the strength of the signal compared to the level of RF noise, with RF noise being anything from other devices that are sharing that spectrum, so your neighbor's Wi-Fi device, your Bluetooth mouse, or just RF interference and noise coming off of industrial equipment, things like that. A good way to think of signal to noise ratio would be the analogy of having a conversation with a friend of yours. If you and your friend are sitting in your living room with no TVs on, you can hear each other very well because the only sound is the sound of each other's voice. You don't have to speak very loudly. Take that same conversation, move that to a nightclub on a Friday night, and suddenly, even if you're talking at the same level, you won't be able to hear each other because of all the background noise from the other patrons at the club, from the music that's being played, etc. So those other sounds that you don't want to hear, that's noise. What you do want to hear is the signal. So what the ratio of volume between those two is your signal to noise ratio. So the better that ratio, the more reliable your Wi-Fi connection is, the better speeds you can achieve on that Wi-Fi connection. And then just attenuation is basically a measurement of how much the signal is degrading. So as the signal passes through things, some of that energy in that radio wave is being absorbed. So that will determine how far your signal can go. If you're talking open air, it can go much further than if it's having to penetrate things like walls and furniture and human beings, trees with leaves, things like that. But even open air, it does degrade because the air, while we can't see it, and unless it's windy, we probably don't really feel it, but the air holds moisture, the air holds dust and other things which do gradually attenuate the signal. So if you want to calculate how far your signal can go, there is the formula right up there on the screen. I am not going to pretend to be able to read it, but that's how you calculate basically how far a signal is going to go from your Wi-Fi device. You can see here it's a logarithmic function, which is again why DBM is probably a little bit closer to giving you an idea of the actual performance difference between products versus the giant milliwatt differences on stuff. And then here we've got some examples of things that are going to degrade the signal and roughly how much signal degradation you should get. So one of the things that maybe surprises people is oftentimes if you're trying to shoot a Wi-Fi beam from inside one building to another building, a lot of people will put it in the window, which seems like it should work right. It lets light through. It should let radio through. But if that window is tinted, or you've got a wireless screen on the other side of that window, you may actually be in a situation where you get a better signal trying to broadcast through some cheap siding between the two buildings versus trying to put it through the window. So when it comes to Wi-Fi range, something that tends to get overlooked a lot is that Wi-Fi is two-way communication. And the power output or the strength or how loud the voice of your Wi-Fi device is, your access point or your router is much greater capability of being loud than your mobile device does. Your mobile device is operating off of a battery, so a lot is done to try to maximize the battery life of that mobile device. And one of the things that they do to help prolong the battery is they reduce how much power is being fed into that Wi-Fi chip. So you run into this situation where, um, you've got a good strong signal here at your mobile device, but your access point or router can't hear that signal. So basically, the weakest member of the conversation is who's going to determine what that range is. This also plays a big part into when we're dealing with office buildings and condos and things like that, where you've got a large number of routers or access points. They can be causing interference in really long ways, much more than maybe you think would be possible, because of just how strong those devices can be. So, a good way, another way of analogy to think about it is, again, we're talking about a conversation between you and your friend. If you're nice and healthy and talking at a normal level, but your friend's got a head cold and borderline laryngitis, they can barely speak, you know, you have to get closer together to be able to have that conversation. Yes, your friend can hear you from across the room, but you can't hear them. So you've got to get closer. Same thing's what's going on here with Wi Fi. One of the other challenges we run into with Wi Fi is that it does interact with the things around it. So we have mentioned that Wi-Fi signal can pass through things like walls and people and furniture, but it can also bounce off of things. So in the real world, you're sending out your signal, it's roughly going out in a circular pattern. It will interact and bounce off of items in your home or in your office. It behaves very similar, radio waves do, to waves in water. So if you think about a pond with maybe, some rocks in it and some plants and some ducks, and you throw a rock into the water and watch how the waves react that emanate out from where you've thrown that rock. It's very similar to what you would see with Wi-Fi. If it hits a large solid object, the waves will bounce off of it. So you'll get the waves overlapping with each other. Waves have the ability to actually wrap around. So they'll hit a solid object on the corner and they can actually wrap around and then broadcast out in a different direction from that. They can hit something and scatter in multiple different directions. So your Wi-Fi device is having to basically deal with what essentially are a bunch of different waves coming in from the same signal. So it starts off as one clear wave here. And by the time it gets to whichever device is receiving that signal, it's seeing multiple different waves coming in at different strengths containing that same information. So that can cause issues in the real world environment for you. The main thing on this is going to be what we call multipath. And so this was something that was the bane of Wi-Fi's existence back in the 11A, B, and G days. And it's something we actually turned into a benefit with 11N. And we'll talk a little bit more about that on a future slide. So when it comes to Wi-Fi, at least before Wi-Fi 7, maybe 6 had some of this too, but this was how Wi-Fi works, and this is still how most of your Wi-Fi devices work. There is no coordination with whose turn it is to broadcast, and each device needs to take a turn broadcasting. So if you've got 30 devices on your wireless network, they're each taking turns broadcasting. And if 2 or more devices broadcast at the same time, it causes interference and that data to be lost. Now, there is technology that we'll talk about called MLO, multi-link operation, which kind of sort of does allow multiple devices to broadcast at the same time. But the core behavior is still based on that. It just gives us a little bit more flexibility. But at the end of the day, we're still taking turns as each device broadcasts. And that's just because there's only so much bandwidth available, and only one device can be using the frequency at the same time. If you've ever gone on a long road trip, you've probably encountered this where you're listening to one radio station back when people listened to radio stations. And you would be listening to one radio station, and as you got away from the town that radio station was in, and you got closer to another town that had a radio station either operating at that same frequency or channel, or operating on a nearby channel, you probably ran into that situation where you would hear both at the same time, or the volume would undulate up and down. That's what happens in Wi-Fi when you've got 2 devices broadcasting at the same time. So the Wi-Fi solution, devised all the way back in 1997 and not changed for over 20 years, was basically, if you want to broadcast some packets, you stop for a second and you listen. Is anybody else broadcasting? If not, you go ahead and broadcast whatever it is you wanted to broadcast. If you do hear somebody broadcasting, you then use a random number generator, back off a certain period of time, and then you start the process over again until you've got a window where you listen and you don't hear anybody else broadcasting, then you go. Now, the challenge that you run into with this is as you add more and more devices and you do things which require more constant data transfer, such as streaming, is it becomes much more likely that two or more devices are going to want to broadcast at the same time. They will both listen at the same time, both detect that no one's currently broadcasting, and then choose to broadcast. So now you've got collision and the data has to be resent. It's been lost. This is compounded in a typical Wi-Fi environment because of something called the hidden node problem. And so what's happening here is you've got your access point here in the middle of the screen, and you've got this circle here. So this blue circle is the area where the access point is broadcasting its signal, and it's where it can hear signal coming from. You've got two different client devices here on each side of the access point, and this yellow circle is the distance that that access point is able to broadcast its signal and hear signal coming from other devices. So you run into a situation here where you've got two devices and they can't hear each other. So as far as they're concerned, the other one is never broadcasting. It's all the airtime is always available. But the access point hears both, and the access point will be able to hear the signal from both. You'll have that conflict, the signals will interfere with each other, and the packets will be dropped, and the clients will be none the wiser. So this is just something that compounds the problem with the way Wi-Fi works. Now, Wi-Fi 7 in particular has got some technologies that help try to solve some of this. But it does require all the client devices also be compatible in Wi-Fi 7. So as long as you've still got older devices connecting to your network, the benefits of some of those changes are minimized. The next thing I want to talk about here, we don't want that, is data rate versus throughput. Let me put my phone on mute because I'm sure the doctor's office will be calling back in just a second. So there's different terminologies used for talking about speeds of network devices. And there's different ways of measuring that. So I'm using the terms data rate and throughput to mean two different things. These are not exclusively the way these terms can be are used out there, but these are the ways I'm going to use them today to make this sort of clear, because this is a problem you run into. All you have to do is go into a Amazon listing for anybody's Wi-Fi product and start reading the reviews, and you will find people complaining. This product says it's a 5 gigabit per second wireless connection, but I ran my speed test and I was only getting 2 gigabits per second. Why are they lying to me? And that's because of the differences between data rate versus throughput, or however you want to define these two terms. And so basically the way 802.11 has always measured speed for any sort of network device is based on the physical rate or the link rate between the two products, the speed they negotiate. So that's what I'm going to call the data rate. So that includes all data that's transmitted between those two devices, including protocol overhead and all the other stuff that goes into making networking work. And in the case of a wired medium like Ethernet, where you've got exclusive wired access, there's very little overhead other than the protocol overhead of like TCP itself. And so there's very little difference, so no one complained. Wi-Fi, on the other hand, is a wireless technology using unlicensed spectrum where it has to share that frequency with a bunch of other things out there that may also be using that same frequency. So because of that, there's interference issues, there's packet drop issues, there's all sorts of other things that can cause problems with transmitting data. So the Wi-Fi protocols have a bunch of overhead that's built in to verify the data transmitted is the same as the data received, to be able to recognize that packets have been dropped and the need to retransmit those packets, and a bunch of other stuff that makes, networking work in a very lossy environment. So because of that, the data rate isn't going to match your throughput. And the throughput is what someone's going to see when they run some sort of speed test, whether they're going to speedtest.net or they've set up their own point-to-point speed test or they're timing an FTP transfer, because all they're doing is measuring the data that they want to send for that test. They're transferring a file of a known size and measuring how long it takes to transmit it. So it doesn't include all this extra overhead that goes into making Wi-Fi work. So because of that, it's very normal to see, the measured throughput is generally going to be no better than half of the advertised data rate, and oftentimes less than that. And as we go into these further slides, you'll understand why there's even more things that go into it. But I mean, just to give you an example, if you're doing your speed test and you're right next to your router, you're going to get one speed. If you're one room over, you're going to get a lower speed because of the signal strength issues. If you've got a Wi-Fi 7 access point and your device you're using to measure the speeds is only a Wi-Fi 6 device, it's not going to be able to achieve Wi-Fi 7 speed. So all of that and a bunch of other stuff that we'll talk about in these next few slides, can further degrade throughput as measured from a wireless user versus the data rate that you'll see on the data sheet. So how do vendors increase speed, or how does Wi-Fi increase speed? As we go from generation to generation, we get faster and faster speed. So let's talk about how we do that. The first one is encoding. So we use something called QAM to measure the type of encoding we do to cram data onto those radio waves. So as we increase the QAM, we increase the amount of data that can be combined onto those radio waves. And you say, well, why don't we just, why does older technology only use 64 QAM or newer technology uses 1024 QAM? And the answer is just, the technology wasn't there. It requires powerful chips to do this encoding in real time. And as we mentioned, a big part of the benefits of Wi-Fi is mobile devices connect to it. So those mobile devices have to have enough power to do the QAM, and they have to have the battery life to be able to support the chip. So the chips need to have the power and the efficiency to make it realistically possible for devices to use. The other thing we do is we increase the number of spatial streams, and we can increase the bandwidth. So let's go through these in kind of reverse order. So we'll start by talking about 2.4. So here in North America, or at least in the United States, I think Canada also. Yeah, Canada also. So North America and Mexico. So we have 11 channels available. In Europe and Japan and some other places, they have up to 13 channels, but in the US, we've got 11 channels available. So that sounds great. The problem we run into is, if you see here, there's very small gaps. There's basically a 5 megahertz gap between each of these channels. The problem we run into is that for Wi-Fi, we're using 20 megahertz channels. So when you choose channel 6 on your device, that's what I want to broadcast on, you're actually broadcasting across overlaps with channels 4 through 8. So because of that, there's only 3 non-overlapping channels in the 2.4 gigahertz spectrum that can be used. So as soon as you add a fourth device, fourth access point, or another Bluetooth device or something like that, you're overlapping and causing interference with your neighbors. So one of the ways we increase speed is by increasing how big of a channel we are using. So one of the benefits with 802.11n was the addition of a 40 gigahertz or megahertz channel instead of 20. But again, we've only got 60 total that's available in the US to use. So that means basically as soon as you use a 40 megahertz channel, you are overlapping with any other device. So now you've got interference issues. So you've doubled your speed because you've got double the bandwidth available, but you've increased the likelihood that you're going to have interference issues, which are going to degrade performance. So one of the solutions to this was the 5 gigahertz space. So 5 gigahertz opens up a bunch more frequency for us. So instead of 3 non-overlapping 20 megahertz channels, we now have, I think it's 26 non-overlapping 20 megahertz channels, right? So a ton more of spectrum available to solve those interference issues. Now you'll notice here that a bunch of these channels are highlighted in orangey yellowy color. What is this? So 5 gigahertz used to require a license to be able to operate and broadcast in 5 gigahertz. So the FCC opened up 5 gigahertz for unlicensed spectrum use. The question was, well, how do you deal with those existing licensed users who are already using 5 gigahertz spectrum? So the technology they came up with was DFS. I think it's dynamic frequency selection. So basically, if a product, an access point or router is going to broadcast on the 5 gigahertz spectrum, it has to listen for existing licensed users before it allows itself to start broadcasting a channel. If it detects a licensed user is now using 5 gigahertz, it has to immediately stop using that channel. So one of the most common uses of 5 gigahertz is radar, but there's all sorts of other things that use it. So the challenge is, if you're using 5 gigahertz, is your customer or your users may periodically be dumped off if your access point thinks it detects a existing licensed user using that same frequency. So it's got to stop broadcasting immediately. Then it needs to check for another channel to use. Then it needs to see if anybody else is already using that channel. Then it can start broadcasting again. So users may see periodic drops. The other problem with DFS is a lot of consumer products don't support DFS. So DFS adds, I don't know if it's still true, but it used to add about 6 months to the FCC certification process. And the consumer face for consumer products, first to market is, often the first to win. So products didn't want to wait those extra 6 months to get their certification. Sometimes they would ship without DFS and then they'd add it with a firmware update, but then users would have to do a firmware update. Most users don't. So because of that, you may not want to be using those DFS channels. We ran into this with one of our customers doing an MDU deployment a year or so ago. They were using Roku sticks to provide over-the-top IPTV to all the users. And these Roku sticks, even though they were the latest model, did not support DFS channels. So you had a bunch of users saying, hey, my Roku stick isn't working, and that's because their access point was using one of these DFS channels. So if you eliminate these DFS channels, which most of you probably will in most deployments, you've gone from 26 non-overlapping 20 megahertz channels down to 8 or 9. Now, as we talked about, we're trying to increase speeds. Everyone wants faster speeds. So how do you do that? You increase the bandwidth. So now if we want to go and double our speed, we go to double our bandwidth at 40 megahertz. And now we've only got 4 non-overlapping channels, but that's still not fast enough. We want to use 80 megahertz channels. So now we're down to just 2 non-overlapping 80 megahertz channels that are available. So as soon as you add a third access point or a third neighbor, you've got interference issues. And then with Wi-Fi 6, we had 160 megahertz channels. So those have to operate in DFS. So the good news is, if your Wi-Fi 6 device supports 160 megahertz, it does support DFS channels. The bad news is there's plenty of consumer products out there that just don't support 160 megahertz channels. And you probably won't find it unless it's on a consumer product, unless you contact the manufacturer and ask them, or you buy the product and just find it doesn't work. For some reason, consumer products don't like to advertise which features they don't support. It's funny. I don't understand. The next thing is spatial streams. So spatial streams, as we were talking about, Wi-Fi signals bounce off of different things in the environment. So what happens is you send out a signal, and that signal radiates out and starts hitting other objects in there. And now that same signal is traveling different ways to get to the same location. So if this was voice waves, this would be like if you shout in a room with no furniture, you'll hear echoes as your sound bounces off of different surfaces in that room. And it's the same thing with Wi-Fi. So this used to be a big problem. Eventually, some people much, much smarter than me, some of who worked at one of Zycel's sister companies, realized that you could actually use this as a benefit. So what you can do is you can send different data on the same frequency at the same time without causing interference, or causing interference, but in a way that can be isolated. So basically what happens is you have multiple antennas. Both are broadcasting simultaneously on the same frequency, but they both have different data encoded onto those streams. And they rely on the fact that if the antennas are slightly physically in different locations, the signal will take slightly different paths in the environment. And that means there will be slight delays between when those signals reach the other side of the signal. So by doing that, you can broadcast additional data and then have it combined together as if it was one faster connection. So these are spatial streams, and this is called MIMO, multiple in, multiple out. So initially, what this allowed was access points to send faster speeds to one client device. You still had to take turns, and the client device doesn't support it. With Wi-Fi 6, they added MU-MIMO, multi-user MIMO, which allowed you to send those different data streams to different users. So you still had the same amount of bandwidth or throughput available, but you can now send smaller amounts of information to more users at the same time. And with Wi-Fi 7, they added the ability for the clients to also then send the data back to the access point. But at the end of the day, there's only so much bandwidth available. There's only so many spatial streams available. So when looking at data sheets for business class wireless products, you will usually see spatial streams listed. You will see something on the back saying 2x2, 3x3, 4x4, etc. So that's telling you how many spatial streams that device supports. First number is the transmit spatial streams. The second number is going to be the receive spatial streams. So on most access points or routers, both numbers will be the same. If it can transmit 3 spatial streams, it can receive 3 spatial streams. When you look at client devices, though, it's usually the opposite. Usually they can receive more spatial streams than they can transmit. So you'll see 1x2 or 1x3 or 2x3. So they aren't able to transmit at the same speed they can receive at. The other thing you will see is sometimes you will see a number here, 2x2, 3x3, or in this example, 4x4, and then a colon with another smaller number after it. So in this case, it's how many antennas the device has to use for spatial streams. And then the number after the colon is how many of those can be used at once. So a 4x4 colon 3 is realistically a 3x3 device. It just has some flexibility for the access point to determine which of those 4 antennas to use for the 3 spatial streams. So it'll only use 3 of them at a time, but based on the RF environment, maybe it can switch between which 3 it's using to improve performance. But essentially that number after the colon is what determines how many spatial streams you're actually using. So to put it all together, to find out your maximum data rate that you can achieve, you combine all of these. How many spatial streams is your access point support, and how many spatial streams does your client device support? What modulation is supported by both sides? Now, modulation, and this is sort of key here, is highly dependent on the quality of the signal. If there's a lot of interference, your device will automatically drop to lower modulation types, because as you increase the modulation, you increase the sensitivity to interference. So even if you've got a good strong signal, if the signal to noise ratio is low, it'll drop back to a slower or lower QAM. And then you look at what sort of bandwidth is available that you're using, combine those all together, and you can figure out what your maximum data rate is. So another common question we get here is, how many devices can I get on your access point? Why does your data sheet say you support 128 devices and your competitor's data sheet says they support 2 million? Why don't you support 2 million like they do? And the answer is really the number of devices that can connect to your access point is a really complex calculation. It has to deal with, how good the RF environment is. What are the capabilities of the client devices that are connected to your access point? What are those client devices doing? What I will tell you is 100% guarantee. You will have users complaining about the quality of your Wi-Fi connection long before you get to whatever number is on that data sheet. That data sheet number of maximum number of clients is a fantasy. It doesn't exist. It's not real. All it is basically saying, hey, we've got this much memory we've allocated to a association table. That's how many devices can associate before our association table maxes out. In the real world, your users are going to be moaning and complaining that the Wi-Fi network doesn't work long before you get anywhere near to that number. And the answer to that is, and why that is really simple. The available amount of wireless spectrum being used determines how many users you can have connected to your access point, realistically. And that doesn't matter what vendor's product you're using. There is no magic sauce that changes that. Wi-Fi is Wi-Fi. Wi-Fi 7 will have its limits. Wi-Fi 6 will have its limits. Wi-Fi 5 will have its limits of how they utilize that airtime. And once you max out the airtime, you've maxed out the airtime. We've got a slide here giving some examples. And all we are doing is changing one variable. We've got an access point. The client has a certain amount of signal strength. It's using 5 gigahertz. It's using 20 megahertz channels. And they're trying to stream a 3 megabit video stream. So they're watching YouTube. And the only variable we're changing is how many spatial streams that client device supports. Our access point supports at least 3 spatial streams. So if we pair it with a laptop, which supports 3 spatial streams, you can get 34 laptops connected to that access point. And no one's going to have any bandwidth limitation issues. You're going to have no problem. You're using 77% of the airtime. If we switch the client device to another client device, same output power, same strength, but one less spatial stream, still watching that same 3 megabit per second YouTube stream, you can only fit 21 of those laptops onto that access point. As soon as you add that 20-second user, your users will start complaining they're not getting enough bandwidth. Go down to a device that only supports 1 spatial stream. You now can only get 10 users on that same access point before they start complaining that they don't have enough bandwidth to watch their YouTube stream. So you can see here just how one variable dramatically changes the number of users that can connect to the laptop or connect to your access point. Why? Because as we reduce these spatial streams, we reduce the speed that the data can be transmitted to the client device. And as you lower the speed, it uses up more airtime. So the airtime is being consumed. And again, we each have to take turns. You have to take turns. So once you've used up your airtime, there is no other airtime. You are going to start interfering and causing issues. So that's why I say, when you look at, how many clients can I fit on there, I can't tell you. The number on the data sheet means nothing. And that's why. So now let's talk a little bit about co-channel interference. I'm going to go through these pretty quick just because we're running out of time here. But co-channel interference is just the term used to mean interference between multiple devices broadcasting on the same channel. And traditionally, the way you dealt with that, you'd carefully do a site plan and try to plot out where the APs are in relationship to each other. And then you would adjust the power output down to minimize the amount of bleed over, right? We talked about that. An access point has a lot more power than the client device. So why not just reduce the power on your access point to more closely match the client device? Now the signal doesn't go that far, so the AP isn't interfering with other APs. The challenge with that is, and it may work, and we will tell you to do this in some tough RF situations, but the challenge is as you reduce your RF power, you're also harming your signal to noise ratio. So you're trading interference issues for worse signal to noise ratio, and depending on the situation, interference may be less of a problem than a worse signal to noise ratio. It just depends. So one of the solutions to that is smart antenna technology. So that's something we've got in some of our access points that end with the letter S. And basically, instead of using a fixed antenna pattern, we have an array that's able to choose from hundreds of different antenna patterns. So it has an algorithm that looks at where the client device is in relationship to the access point and also where other sources of RF interference are coming from. And it can choose optimized antenna patterns to optimize both for client placement and where other sources of interference are, so those interference signals don't interfere with the AP's ability to hear the client device. It makes a huge difference in tough RF environments, condos, expo centers, business, large open spaces with either lots of users or lots of access points. And the great thing about smart antenna, other than beam, which makes it different than beamforming, is it works with mobile devices as they move around. So we did a real world case study that we did back in the day. So I will compare it here. We compared one of our access points with a Ubiquiti access point, which on paper were basically the same. They were using, I think they were even using the same Wi-Fi chip, same output power, same channels. The only difference is we had smart antenna and they didn't. And we set it up in this hotel environment where you've got these access points in each room. They're using 5 gigahertz. So you've got a number of different channels to choose from. They are using non-DFS channels because you don't know what the hotel customer's, client device is going to support. So you don't have any rooms directly next to each other using the same frequency, but you do have them nearby. So when we had one AP going using our smart antenna technology versus the Ubiquiti device without smart antenna, performance was basically the same. Ubiquiti technically beat us by a couple megabits per second. As soon as we added a second access point operating on that same channel, you start noticing a big difference here. So you will notice we were able to achieve an aggregated 785 megabits per second throughput between those two APs, where Ubiquiti maxed out at 555 megabits per second. And you will notice we were able to achieve a greater than 100% airtime utilization across those two access points. How? Because the smart antenna allowed both access points to function at the same time using the same channel without interfering with each other. So the aggregated airtime utilization was 131% with smart antenna versus 95% with Ubiquiti. Now we add a third access point in there, and you will see aggregated throughput increased a little bit more. Airtime utilization with smart antenna increased more. And Ubiquiti had actually got a little bit worse because of all the retransmits and fighting that was being done. Another big difference you will notice here is that the throughput is pretty evenly distributed between all three access points. Whereas with the Ubiquiti, and I'm not picking on Ubiquiti, this would be true of even our own non-smart antenna access points. Without the smart antenna, you see that it's much more lopsided, with some access points doing a little bit better job of fighting for that airtime than the other ones did, because it's just sort of a free-for-all, where smart antenna helps democratize things. So smart antenna, very important for tough RF environments, makes a huge difference. So we'll talk a little bit about Wi-Fi 7. Again, I'm going to go really quick through this because we're running out of time. And that is, again, one of the main benefits of Wi-Fi 7 and technically 6E is support for 6 gigahertz. So before we had 2.4 and 5 gigahertz, this is the amount of available bandwidth that everybody has to share. This is 6 gigahertz. So 6 gigahertz has more bandwidth than 2.4 and 5 gigahertz combined. That's why 6 gigahertz is a huge game changer for us. It solves a lot of these interference issues that have plagued Wi-Fi deployments forever. So we do have to keep in mind some things about 6 gigahertz. One is it's a higher frequency than 5 gigahertz, so the range is going to be less. So if you're just swapping from existing access point install to new 6 gigahertz access points, you may need to add a few other access points or rearrange where you've got them located, because the 6 gigahertz footprint will not be the same as the 5 gigahertz footprint. And not all Wi-Fi 7 devices support 6 gigahertz, right? In order to keep prices down, a lot of products still only support 2.4 and 5. Keeps the price down. You don't need as powerful of processor. You don't need 3 radios. You don't need 3 sets of amplifiers, 3 sets of antennas. And also, a lot of users don't have very many devices that support 6 gigahertz properly. So because of that, you may not need it, but just keep that in mind. Just because it's Wi-Fi 7 doesn't mean it supports 6 gigahertz. And then the other thing that goes into it here is with 6 gigahertz, you have to use specialty outdoor equipment to deploy outdoors. You can't just take an indoor AP and mount it outside inside a plastic box somewhere like you could with 2.4 and 5 gigahertz products. In order to use 6 gigahertz outside, you have to use something called an AFC, where your access point has to be able to use GPS to geolocate where it's at. It has to check with a third-party service to see which licensed users, because again, 6 gigahertz has users that have been using this for all these years that have been paying for a license. So it has to check which licensed users are nearby, and then it will determine whether or not what channels it can use based on where it's physically located and what power outputs it can use. So because of that, you need specialty equipment or specially designed devices to use 6 gigahertz outdoors. So some of the benefits here of 6 gigahertz are even wider channels. So Wi-Fi 6 gave us 160 megahertz channels. We now have 320 megahertz channels available. We've increased QAM from 1024-bit QAM to 4096-bit for about 10, I think it's 10 or 15% better. More data can be encoded now with this. Multi-link operation. This is a great new technology. It allows a client device to simultaneously connect to multiple radios on the same AP. So you can be simultaneously connected to all three, if your device supports it, radios in your access point 2.4, 5, and 6 for faster speeds, better latency, and better able to tolerate interference. Because if one of those radios is experiencing interference issues, you just pipe the data through one of the radios that's not. So 6 gigahertz is really important for high density environments and for technology where you either need low latency, high bandwidth, or both at the same time. So when looking at Zycel products, we often get questions asking what the difference is between the NWA and the WBE series. And I do cover this in a little bit more in depth on our Meet Our Access Points webinar. But just the short version, the NWA products, the 50 and 90 series are sort of our Soho consumer products. The 100 and 200 series are our business class products. Then we have the W series. So for the business class NWA versus the business class WBE products, the W products include Nebula Pro Pack, a 1-year license is bundled with them. The W series supports the ability to interface with our USG Flex and USG Flex H series. So those can be used as a local controller with that. It can also be used for additional security services on the access points that coordinate with the security gateway. And then the W series is where you're going to find some of our advanced antenna technologies, like the smart antenna that we talked about earlier. And it also gives us support for things like secure Wi-Fi, GRE over IPsec tunneling, things like that. Otherwise, they're basically the same. So one other antenna technology to talk about here really quick would be our dual optimized antennas. So this just has to do with, antennas are optimized, or access points are optimized with the idea that you're mounting them on the ceiling over the area to be covered. In the real world, you often end up mounting these on walls, so the signal ends up not being optimized. You end up sending a lot of signal up into the ceiling or down into the floor, where the signal is lost, or if it's a multi-story building, maybe you've got interference between the floors. So we do have a technology called dual optimized antennas that some of our access points have, where we have 2 sets of antennas, one that's optimized for the ceiling, one that's optimized for the wall that you can switch between. So just as a general rule, when it comes to mounting, again, these APs are optimized for ceiling mounting over the area to be covered. So that's when, if you can, that's where you should be mounting your typical access point at. And generally, the higher, the better, within reason, because that minimizes the amount of obstructions that signal has to go through. So the higher up the AP is, the more vertical the signal is, so the less likelihood there is to be obstructions. Whereas it lowers, the more likely the signal has to pass through things like people or cubicle walls to get to the access point. So if you're mounting it, if your local building code allows it, mount the access point above the drop ceiling. Your typical fiber drop ceiling has very little attenuation. So that way you can mount the access point above the area and you don't have to poke holes in the drop ceiling, which I know a lot of end users don't like you poking holes and running wires through their drop ceiling. So if your local building code allows it, just, rest the AP on top of the drop ceiling. When you are mounting it above a drop ceiling, do take into account ductwork, lighting, and other things like that. Wi-Fi doesn't like metal. So if you mount it up on the true ceiling right next to some electrical conduit or next to some AD vents or AC vents, excuse me, it's going to cause issues. There are third-party standoffs you can buy specifically designed for mounting access points to, which drop them down from the ceiling to avoid all those things that are usually bolted to the ceiling in commercial environments. So in a hotel environment, in the old days, we used what was called umbrella coverage. You would mount some access points out in the hallway, and they would cover anywhere from 4 to 8, or in some cases, 16 rooms. I have seen that done. That worked great in the old days when, people had 1 or 2 Wi-Fi devices. These days, people are offloading a lot more devices or bringing a lot more devices with them on the road, and they're using those devices instead of just checking email and emailing a couple spreadsheets for work. They're now using that to stream video and things like that. So that doesn't work. The signal isn't strong enough getting back from the far corners of the rooms to the access point out in the hallway, right? It's got to pass through two walls and very often some metal pipes or conduit in the walls through the bathroom. So most newer hotels now are deploying one access point per room or one per every other room. And us and everyone else make special wall mount hospitality APs specifically for doing this. The access points are a little bit lower powered, so you don't have the interference issues since the signal doesn't need to penetrate multiple walls. And it just works a lot better for users. Um, so, one thing to keep in mind when you're doing this is people will steal the access point if they can. So you often want to hide the access point if you're installing it in a room or use some form of locking mount, which ours have a basic locking function, which the typical user won't be able to easily figure out, just to help reduce the risk of somebody stealing the access point. And then you should turn off LEDs on the access point if it's mounted in someone's room because no one wants flashing green or blue lights while they're trying to sleep. Other things to keep in mind is basically plan out each area of the hotel separately. You know, guest rooms are separate from your conference center, which are separate from your meeting rooms, which are separate from the lobby. So plan each of those as their own environment based on the needs of the users and the hotel in those environments. You know, use load balancing, use client steering to help prevent AP overhead, and make sure you are setting up load balancing groups based on the geographic location. Excuse me. We have encountered people that left the entire hotel as one big load balancing thing. So it was trying to push users from the lobby to, you know, somebody's guest room on the fifth floor. So you want to create your groups in Nebula or groups on your controller to be able to better control where the where it's going to try to push people to. And in those really tough high density environments like meeting rooms and stuff like that, use smart antenna. It makes a huge difference. School strategy. I mean, the main things you're looking at is, one, is it a smart room? Are they actually going to be using, Wi-Fi pretty consistently in the room? A lot of rooms, people are only getting on the Wi-Fi for doing, research or to take their tests and submit their paperwork. In other rooms, teachers are live streaming video to every single student in the room. So find out how they're using the Wi-Fi in the room. It may make give you some ideas of what you need to design and engineer for. These days everybody has a Wi-Fi device. I think that's pretty much a given at this point. But look at how many users are going to be in that room, and again, how they're going to be using the Wi-Fi. You may need to have two APs in the room if you've got a room with 50 or 60 students, or if you've got a room with only 20 students, but they're video streaming simultaneously to all of the Chromebooks in the room. You may need two access points per room. On our Nebula interface, we do have a special load balancing mode that's designed specifically for school deployments, with the idea that you'll have 30 or 40 students simultaneously connecting to that access point at the same time. Wayne's asking about smart antenna. So Wayne, when you look at our model numbers, if it ends in the letter S, it has smart antenna. So WBE660S, the S means smart antenna. That's how you're going to tell. And be sure you don't put the students and the teachers on the same network. These should be VLANed off from each other. They should have their own SSIDs, and they should be completely isolated. Otherwise, teachers will get hacked. It happens. And lastly, I wanted to talk a little bit here about Wi-Fi 8, just to let you know it is coming. As I mentioned earlier, the certification or ratification of the standard isn't expected until probably 2028 at the earliest, and I would not be surprised to see it slip to 2029 or 2030. You will see consumer products claiming to be Wi-Fi 8 by the end of this year, and you will probably see business class products calling themselves Wi-Fi 8 in the first half of 2027. The primary difference, because we're out of time here, but the primary difference between Wi-Fi 8 is the features that were originally promised for Wi-Fi 7 Phase 2 are now just being called Wi-Fi 8. They've been pushed back to just to be part of Wi-Fi 8. So instead of having Wi-Fi 7 phase 1 and phase 2, now you have Wi-Fi 8. And that main feature is the ability for a client device to simultaneously connect to multiple access points. So instead of being limited to one access point that you're connected to, it will connect to two. It also allows the access points to communicate with each other and help coordinate for load balancing and to help with that sticky roaming problem that we often run into, especially with iOS users, where the access point doesn't, or the client device does not want to roam. This would allow the access point to figure out, hey, this client device, he should probably roam. I'm going to kick him off because I can see that there's another access point closer to him that he'd have a better time with. And with that, guys, we are done. So if you have questions, send them in using chat or the Q&A, and I will stick around for another couple minutes here. I do have another call I've got to jump onto, but I will stick around for just a minute. And of course, you can always email me. My email's up there on the screen now, seanr@zycel.com. Or if you're on this webinar, you're probably one of our reseller partners. You can always reach out to your salesperson. They have access to me. They have access to Try. They have access to our sales engineer who knows a lot more than I do. So feel free to reach out to them and they'll get your question answered or get it forwarded to the right person. I am not seeing any questions coming in, so I am going to go ahead and end today's webinar. Again, if I'm ending it too quickly, just drop me an email or reach out to your salesperson. Thank you for joining us today, and I hope I see you on one of our future webinars. Thank you.